All right. Good afternoon, everyone. Welcome to re:Invent 2025. Today, we have an exciting presentation for you on the evolution of generative AI and agentic AI at the edge. As many of you have heard, AWS is making a lot of advancements when it comes to running your AI workloads in regions. However, there are a number of customers who cannot deploy their workloads in regions either because of data residency, their compliance needs, or low latency. And that's why we are here to talk about how you can harness the power of agentic AI and generative AI and drive innovation at the edge. I'm Pranav, and I'm excited to be here with Fernando and Chris. So over the last few years, we spent a lot of time helping our customers design and architect their application workloads outside of regions. And this hands-on experience has really provided us unique insights into challenges and opportunities in this area. So in this session, we'll share our practical guidance on how you should think about deploying your edge-based AI workloads. And I just want to clarify, our intention is not to provide one-size-fits-all solution. We want to provide you the right framework, the right optionality for you to best architect your applications and your workloads. So let's get started. We have an exciting agenda lined up for you today. First, we're going to start by unpacking what we mean by generative AI and agentic AI. Next, we'll talk about some of these use cases that are already driving tangible business value for our customers. And then building on that foundation, we'll talk about how you can optimize pre-trained models to run efficiently at the edge. Optimization is only half the battle, so we'll also talk about how you can enhance the accuracy, how you can improve the performance of these models as well. And then finally, we'll dive deep into how you can deploy agentic AI workloads to run efficiently at the edge as well. By the end of this session, you'll walk away with a comprehensive understanding of how you should deploy your edge workloads to drive innovation with AI and agentic AI. So before we go through some of the use cases and various AWS offerings, I wanted to walk you through some of the journey that we're seeing with our customers who are using generative AI at AWS. Overall, I'm super impressed by how far we've come along, especially in such short amount of time. So if you look at year 2023, this was a year of POCs. Customers were still doing testing. They were trying to figure out what they can do with generative AI. And then in 2024, we saw a big shift. This is where customers started focusing on prioritizing real-world use cases, focusing on the business outcomes they can drive. And here we are in 2025, where customers are really focused on driving the business value while still caring about the things they should care about, including security, privacy, and just doing it in the right way. And a big shift we have seen in the last couple of years is also customers thinking about more and more AI workloads to be deployed on-premises or at the edge. And the journey doesn't really end here. This is where we're seeing a next evolution of agentic AI systems, and that's where things get really interesting. So let me just talk about what we mean by generative AI agents before we jump into agentic AI systems. So generative AI agents are much more goal-oriented. They can handle a much complex range of tasks compared to generative AI assistants. They can really automate your entire workflows without a lot of human intervention. At the same time, they can evolve to changing ecosystem. On the other hand, agentic AI systems are fully autonomous. This is where agents can interact with each other. They can make really complex decisions and really mimic human-like reasoning capabilities. So when you think about deploying your AI workloads, it's really important to also think about how you should leverage the power of agentic AI systems to improve your business processes. As I mentioned, in this session, we'll cover both generative AI and agentic AI systems. So before we dive deeper into use cases, I wanted to walk you through the AI continuum and various AWS offerings that exist in this space. When people think about deploying their AI workloads, they tend to think about two options. It's either regions or it's on-premises. The reality, it's a much more nuanced conversation. In fact, we're seeing a lot of enterprises asking for a consistent experience when it comes to on-premises, regions, and even edge deployments. So how are we meeting the requirements of these customers who have varying deployment needs? We're basically doing that by bringing AWS wherever our customers need them. So on the left side, you see AWS regions, which are available in 38 locations. They continue to provide you access to the latest and greatest NVIDIA GPUs, our own Amazon accelerated chips, including Trainium and Inferentia, as well as high-performance storage, and EC2 Ultra clusters that really provide you petabit scale networking. In these regions, you also get access to the AI services like Bedrock and SageMaker. And then when we shift towards the right, this is where we have AWS Local Zones, which are available in select locations like Atlanta, Dallas, and Phoenix. These local zones provide you similar experience to some of these regions with high concentration of NVIDIA GPUs, our own Amazon accelerated chips, as well as EC2 Ultra clusters and high-performance storage. 2 days back, we also announced something called as AWS AI Factories, which provide you very similar experience in some of these regions and these select local zones as well, but in your own data centers, in your own on-premises facilities. And we'll talk a bit about what we mean by AWS AI Factories in the next slide as well. But if you look at all the three offerings I discussed, regions, these select local zones, and AWS AI Factories, they provide you a consistent experience that allows you to deploy any kind of AI workloads, whether it's AI inference, fine-tuning, or even training as well that requires a lot of GPUs in a single location. And then on the right side is what we call as the edge. This is where we have other local zones which are distributed across multiple locations globally. These local zones provide you access to compute and storage without the need to run your own data centers. We also have AWS Outposts and Dedicated Local Zones, which provide you a similar experience, but in your own on-premises. And then we have AWS IoT offerings, which are meant for the far edge. And when you think about all of these edge deployments, they're best suited for the inference and fine-tuning workloads. Overall, across all of this AI continuum, one thing which we made sure is a consistent experience when it comes to services, APIs, toolings, as well as infrastructure as well. So now that you've understood the AI continuum, let's quickly talk about what are these AWS AI factories before we jump into the use cases and some of the business drivers. So these AWS AI factories are dedicated deployments that combine the latest AI chips alongside EC2 Ultra cluster, as well as high-performance storage like FSx and S3 Express One Zone. Overall, these AWS AI factories allow customers to rapidly deploy their AI-powered applications while still meeting their digital sovereignty requirements. We deploy these AWS AI factories in customers' data center, leveraging their own power. At the same time, customers also have an option to also use their own GPUs, their own network connectivity here, which basically allow customers to make use of any investments they've made in this space and really help us meet customers wherever they are in their AI journey. Another key part about these AWS AI factories is the access to the AI services like Bedrock and SageMaker. So with these services in AWS AI factories, customers can gain access to the foundation models without the need to negotiate contracts with different model providers here. At the same time, these AWS AI factories are connected back to the region, which means that customers would get the same security, the same privacy, and the same tooling that they used to on AWS Cloud. And as I mentioned, AWS AI Continuum provides customers a consistent experience all the way from the regions to the edge. And when it comes to the edge, there are three key business drivers that we see across all our customers. The first one is around data residency, where customers with certain regulated workloads cannot deploy these workloads in regions. It's either because of country-specific residency requirements, or it's either because of country-specific sovereignty requirements. Overall, there are limitations on moving and processing data outside of certain geopolitical boundaries or geographical boundaries. And then the second business driver is around corporate policy, where certain corporates or enterprises just cannot deploy or run their data, especially model weights outside of their own sites, their own on-premises facilities. And then the third driver is around low latency. This is where certain customers with certain workloads just cannot tolerate the latency they get by deploying these workloads in distant regions. Overall, all these three key factors, including data residency, corporate policy, and low latency, they really form the foundation business drivers behind why more and more customers are thinking about deploying their AI workloads at the edge or on-premises. And across all these three business drivers that I discussed, customers across a variety of industries are using these edge deployments for a variety of AI use cases. However, from the architecture perspective, they tend to fall into three big categories. The first one is around enhancing customer experience, where a great example is a chatbot, where customers are using generative AI from all the way up to the general purpose bots to industry-specific bots. We've also seen another great example of call center support, where call centers are looking to use generative AI to transcribe audio calls into text call and really analyze those for insights. We are also seeing a lot of customers looking at generative AI to do sentiment analysis and really understand interactions between their own customers. And then the second category is around driving productivity and creativity. This is where a great example is what we are doing internally in Amazon as well, where after every call, after every meeting, we would transcribe voice to text and summarize the key decision, key action items, and the next steps we discussed in a specific meeting. Another great example of use case is content creation, where we are seeing strong uptake, where customers are looking to use generative AI for the first draft of their marketing collaterals, their sales assets, and even other text-based assets as well. And then the third category is around optimizing business processes. This is where recently a bank reached out to us, and they were looking to leverage generative AI to slash the cost and time it takes for them to generate monthly critical business reports. And that's another great use case where we're seeing strong uptake from customers. In fact, the use cases that you see in yellow are the use cases where customers have already moved from POCs to production, while the other ones highlighted in the slide are the use cases we're still working with customers on testing and POC. So now that you've understood the use cases and the business drivers, I'll invite Chris on the stage, who will talk about how you can optimize pre-trained models to run efficiently at the edge. He'll also talk about how you can improve the model accuracy and drive performance with these models as well. In parallel, Fernando will talk about and run you through the demos and really bring all of this to life. And one thing before Chris starts, I want to clarify is, after the end of this session, we'll make sure you have access to the codes of our demos as well, so you can try it yourself and just relive the excitement here. Thanks. Not yet.
Can I get the mic on? Try that again. Yeah, that's working now. So good afternoon. I said we'd like to share with you our journey for the last year, where we've been working with customers to deploy edge use cases for generative AI, and we've jointly learned a lot of lessons as we went along. The format we're trying to show is explain the technology, show the architecture, and then show a demo of the system so you can actually see it working in real life. As my colleague mentioned, at the end we will be around for questions if there's other stuff you want to talk about. So the first thing to look at is the whole area. So the business drivers, as we talked about, are self-managed SLMs where customers, for various reasons, have to manage the generative AI application on-premise for data residency, transparency, etc. What we've set out to do is create a cookbook where you can actually leverage this system not to run a specific model, but actually the cookbook allows you to choose relatively any model on Hugging Face and actually apply this methodology and architecture to it. We've went with the Llama CPP framework because it gives us a very lot of controls on how to run the models, but more importantly, it allows us to compress the model, get it into a small area, because running at the edge, power, cooling, GPUs are all commodities that are scarce and hard to get hold of. So in the work we've been doing for the last year, we've gone from we've improved the performance of the models using this framework by about 5x. So we started off with a few tokens per second. We're now up to 40, 50 tokens per second for exactly the same SLM running in exactly the same GPU. So the first thing to think about when you're entering this engagement is the model selections. How do you actually pick a model? What we found, looking at the left of the slide, is each model is strong at different things, especially if you go down to small language models where we define the small language model as less than 10 billion parameters. We've actually found that certain models like Mistral and Phi are really good at mathematics. Qwen is very good at text generation, etc., but also very good including specific languages and specific domains. So from a deployment strategy, the first thing to decide is how you're actually going to deploy the model. Do you want to go for an LLM strategy where you have an enterprise LLM running on hundreds of GPUs, or do you go with the industry trend of having small language models that work on a particular task or a particular system? Then what we've learned over the last years is really important to understand what you want the model to do, not just at the high level, but in detail. You need to have really good evaluation criteria, and the use case needs to be defined to a fairly low level. Then you've got choices to make. Like the choice is how much tokens per second do you need? You can have a very small language model that has a huge number of tokens per second, but its accuracy is not that great. Or you want to balance the context size that you're feeding into the model, because what we found is larger context size seem to slow down the models, or quantization of the model to squeeze it into a smaller footprint. We have customers that are experimenting on voice to text, for instance, on CPUs, not even GPUs. And we always recommend, as a best practice, start with a small model, try it, see if it works, and then go to the next size up, the next size up, the next size up. Because what we found, a lot of customers start with an LLM, it works fine, and they don't actually see if they could use a smaller model to actually get the same accuracy and performance. And the last thing to do is to look at the sustainability and TCO. I had one customer last year that basically had a manual process it's a financial services bank. They had a financial report they have to run every month that they use humans to pull it together because there's no shared index on the databases. It's basically a hard report to generate. They actually started off and went for a large language model, and the cost to do it manually was $60,000, roughly. When they went to the LLM, it worked fine. They got about 80% accuracy with not a lot of work, and they're quite pleased with that. And then they discovered it was $120,000 to actually pay for the LLM running the tokens. We got involved, and then they deployed a small language model, went through the process we'll talk about in a second, and got the whole thing running for about $7,000 or $8,000. So they actually had a good TCO. And that's what we're trying to say here is it's really important to understand the whole ecosystem you're working with and not just go for the biggest model you can find that does the job. Oops. Sorry, wrong button. So this is the architecture we'll be showing you. We've got 3 levels of this architecture. This is the one we're starting with at the moment. Starting on the right of the diagram, we have the users where basically they present a prompt to the system. We have an application load balancer that load balances across a number of application servers. The application servers themselves are actually doing prompt engineering work, so they're actually taking the prompt, enriching it with a prompt template, and then if it's a real-time application, such as a chatbot, it goes through an ALB into the models. We also have text summarization, text generation use cases that use the same architecture framework, just a different context and a different training on the LLM, and that goes through a queuing mechanism into the system. So the architecture basically is designed to support a range of different use cases and give you a scalable system from one user up to hundreds or thousands of users. Oops. The other thing to say is we had a lot of discussions with customers where they wanted to go for a really large GPU, then they got into the issue of having water cooling, etc. And this was a test result we did with one legal firm where they basically had ingested all the legal text. I'm not a lawyer, so I don't know exactly what they were doing, but they had all the text in there, and they were actually using chatbots to advise the solicitors in the company and respond back. What the white line here shows is the required performance, which is, they defined 6 tokens per second as the requirement. And you can see, starting with 1 user and running up to 48 simultaneous users, all the models we're testing here. And these are just a sample set of the models we test. We test models, different models all the time. And then you can see around 48 tokens, simultaneous users, it starts dropping off in terms of tokens per second, where some models were all able to keep performing up to 64. The model they picked for their evaluation topped out at about 50. So a scaling system was they had up to 10,000 people using the model. They worked out that they had a 1% or less than 1% simultaneous users, so they basically just were able to multiply the number of users by 50 to give the GPU sizing. I'll now hand over to my colleague Fernando to do a demo.
Thank you, Chris. So now we have this Python application that is used to demonstrate local inference at the edge. This is a naive Python. I'm not using any framework to develop. And here you can see that we are using a 5.4 model. It's a 3.84 billion parameters. It's a very tiny model for this kind of application. We have system prompt here when one topic that's very important to treat that is related to prompt engineering. So we take care about some use case here. And also we have the temperature, top P, top K, just to demonstrate it's running at the edge. Talking about the instance that we have behind this application, we can see that we have 4 G4 DNX large, so it's a small GPU. We use 1 GPU Tesla T4 per instance. And we also have the application and the vector DB running in EC2. These EC2s can be deployed in a local zone and also in Outposts. We are not using anything specifically from the region. If I ask a question here, like, what is service link? You can see the answer. That's very fast because we are working with a very tiny model. And here we have some metrics about the input tokens, output tokens, latency, and tokens per second. Another interesting part that we can do is, this is where I'm running Llama server, Llama CPP is the Llama server that we are using to run the local inference in that case. And from this side, I have the chatbot. On the top, you can see the memory, the GPU memory in use, and the utilization. Okay, so if I ask the same question, what is service link? You can see the utilization. Okay, they start consuming, and after that stopped. So it's a very fast model for this use case. And as Chris mentioned, it's a best practice to start using a small model in that case, and we start testing, and you find the right model that it's important for your use case. So another topic that's important is related to the temperature. One thing that we observed here is when we work with big models and we would like to have more creativity, you can increase the temperature. So we start with 0.7.8, sometimes 0.9. When we work with small models, we need to take care because they can start hallucinating very easy. So it's a parameter that if we need to take care when you define the right value. That's the way that you need to be to have the evaluations process inside to detect and to find the right value for this kind of parameter. So the architecture here, we have Milvus running as a vector DB. We can also run using RDS, Postgres, NPG vector, you can enable this extension if you wish, or different database vector DB that you can run. We are using re-rank, another instance that we will explain later in this presentation. The SLM that we use to run Llama server and the 5.4 instruct, and the vector embeddings. It's another module that we use that's part of the RAG that we will explain in a few minutes. So now, Chris, you go ahead with that.
Thank you, Fernando. So what we showed hopefully here is a framework for running efficiently the models. And the first part of our exercise we started off probably 2 years ago was how to get models running really efficiently at the edge with a low cost of ownership. What we found this year is customers have come to us and saying, well, 70% accuracy was great last year, but I want 95% this year. And the next set of slides we go through is how do we actually take a generic model and get it ready to actually provide really high levels of accuracy in terms of the operation. So we strongly recommend that for all deployments, particularly at the edge, you can strongly consider prompt engineering, using a RAG database, and also optionally fine-tuning, because some models don't actually need fine-tuning for a particular task. Sometimes they do. And what we also say is basically any retraining of the model where you're actually doing open heart surgery on the model and reworking the complete thing should be done in the region. And we advise our customers on creating synthetic data where they're not exporting their InfoSec information or rejecting the data to train the models in the region. And that's a strategy for regulated markets that works quite well. So starting off with prompt engineering, as I said, Fernando just showed you a snippet at the moment, but it's really important, and it's also described as a dark art, where you actually need to go through and tell the model what you want the model to do. That's the art of prompt engineering. You need to give it instructions to say, respond with 10 words or respond with 1 word. You can control the model in great detail. You need to give it a context. And one of the funny things we found recently in terms of context is we have an AWS product called AWS Wavelength, and we asked the question, what is wavelength? And the model came back and gave us the physics definition of the speed of light. It had no context that we were actually asking about an AWS product. And that's where context is so important. You need to really guide the model into the behavior you want. The user input is really important in terms of who the user is, what they are they non-technical, technical, etc. And also you can add a security component to say what they can actually access and not access. And then the output is the tone and style. I want an architect response, or I want an engineering response, or I need a lawyer's type response, or in our demo you'll see later, a chef's response. All that can be controlled by the prompt engineering side. And you can also have must-haves in there. You can say, if you don't know the answer, don't make it up, or all this sort of thing. And the other thing we do with our customers is fine-tuning, where we recommend parameter-efficient fine-tuning as the method, where basically you take the model, freeze most of the layers of the model, and then work on a few layers to change the weights being the data effectively in the model, and actually equip the model to be able to respond, say, in a chatbot environment or a summarization environment, etc. So we're going to show you the architecture now of all of this working. So you've had a quick snippet of the context engineering already, but we have 2 slides here that shows the RAG architecture. On the right side of the slides, we have a number of data sources, everything from a file repository with a PDF in it, or Word documents, databases. A lot of our financial services customers are actually using this to access data around customer accounts, information, etc. We also can reach out to the internet, you'll see in the later demo, and also the external data sources like data lakes, etc., and pull that in. The ingestion process detects that is an application running on a EC2 instance, detects there's a new file or a new set of data, pulls that in. If it's a PDF, it also does the chunking strategy for the PDFs, because you don't want to put in a massive file as one chunk. You break it into maybe 4 chunks per page, etc. That's then fed in the right format into the embedding model, and the embedding model basically converts it to a vector alongside the chunk, and they're both stored in the vector database. We're showing PG vector here on RDS Postgres, but we also have a demo using Movis and others. The architecture is not fixed on any particular type of knowledge base. So then, once you have the system up and running with the RAG database, consumers come in and they issue a question or a prompt. That hits our application that does the prompt engineering, etc. Then it sends the prompt to an embedding LLM, or SLM, I should say, that basically creates a vector. That vector then is used to do a top K search. In our case, I think it's 25. We've got as the output, so it gives the nearest 25 chunks that it has in the database to the query. And one of the things we found with that was a lot of the SLMs were getting confused because they were being hit with a lot of data, and they were also, some of the top chunks may have a similar vector, but they may be incorrect data. So both of those things were confusing the model, because it would have to go through all 25 chunks, work out when it's doing its inference which were useful, which weren't. And that caused a lot of inaccuracies. So we introduced this idea of a re-ranker, where we take the top K output, feed it through another SLM. That SLM goes through and does 3 important things. One is it detects bias in the responses from the knowledge base. It also can put any guardrails you have in the system. So you may not want to expose this type of data or something like that. You can set all that in the re-ranker, and it, more importantly, goes through and filters the list that you have from the knowledge base and says, I only want to send these 2 fragments to the SLM that's doing the inference, because the rest of them are not that relevant. And it has a really big impact on the performance of the SLM, because it's not going through 25 chunks now, it's just looking at 2, and it's not having to work out if some of the chunks are misleading it in some way or other. And then the application packages up the prompt template, and the top K chunks returned from the re-ranker, and then we go through the process of the inference and return the answer. With this architecture, I would say we are getting really good results on small models, like certainly 7, 8 billion models down to 2, 3 billion models. They're actually performing at 90, 95% accuracy all the time with very little hallucinations. So our customers are actually really surprised and happy, and we get into lots of discussions with data science teams about how we're managing this with this architecture. So just talk about the re-ranker a bit, because it's one of the new things we've done. So normally in a semantic search, you basically, application calls the semantic search, and the knowledge base goes through and selects the vectors as close as possible to the incoming prompt. And then that's returned to the application. As you can see here, you have, say, I'm using 5 chunks in this example. We have the 5 chunks that's added to the prompt, and then the 5 chunks plus the prompt goes to the SLM. What that means is the SLM has to process a large context size, because all 5 chunks are in there, and more importantly, some of these chunks may be misleading, so that the SLM has to go and think about it more than it would normally. By doing the re-ranker, we actually feed it through another system, and then we can filter the list down to, in this case, 1 response that's really relevant. That means that the context going to the SLM is really small, and it's really accurate in terms of it augments the prompt. And we found that this has a really beneficial setup. And you may ask, why not do all the search in one go on the knowledge base? But what we found by doing it in 2 steps, we could actually do bias detection and have guardrails on it, but also it was faster than doing a really complex lookup in the knowledge base in one go. Now hand back for demos.
Thank you, Chris. So We also have a compare mode here to show the use of RAG and without RAG running at the edge. This application is running exactly the architecture that Chris presented in the last slide. Just remembering, we have two instances, one that we use to run the inference with the context of RAG, and another one that we are using without context. And if I ask a question here, on one side, I expect, on the left side, we can see inference running without RAG. On the right side, we have with RAG. So I can ask the question, what is the same? What's service link? And in this RAG environment, we ingested AWS official documentation about local zones and outposts, and something about bedrock. So when I'm asking about service link on the system prompt, we work to define the chatbot that they can have the responsibility to use this information to answer the question. So we can see here what's service link. From this side, we can see service link is an AWS Outpost facility, customer VPC traffic between the outposts and associates there. If you see another side, we can see the model hallucinating because they are using information inside the small model. They are not using the accurate answer, they are accurate information. From this side, we also have the source used, and here we can see the chunks that we are using. The distance on the RAG, the naive RAG, in that case you can see this chunk, the distance, the similarity in that case is 19%. After the re-rank, reclassified this chunk to 99%. What makes sense? The same for this. So now, instead of 26%, now we have 92. Instead of 27, 90%. So the re-rank is running here to reduce hallucination, to reduce the amount of noisy that we send to the model. So if we send for small, when we work with big models, the big models can handle complexity, so they can understand what's noisy, what's not, and they can provide an accurate answer. When you work with small models, you need to take care, because it's not a thing that the small model can do. And they can start hallucinating very easily. And we tested with different data sets, in that case, and we could observe exactly this behavior. Okay, Chris?
Yep. So just to finish off that section then, what we're saying is we've gone through this process multiple times with customers. First is, it's really worthwhile spending time on the evaluation criteria and creating a good quality data set that we can use for fine-tuning, but also to check the model and make sure the model is behaving correctly. Prompt engineering, as we said, is really important, and it's the context for how the model is supposed to behave. It's your guide to the model. And you can also, in the demo we have, you can also see the instructions say, don't make stuff up, if you don't know the answer, respond, I don't know the answer, etc. And then using RAG is really good for getting data, fresh data into the model where you don't have to retrain all the time, but it also helps the accuracy of the model, especially in the small language models that we're deploying at the edge. And then we go through an optimization process and the testing process. That's the blueprint we've successfully rolled out into a number of customers now, where we're doing everything from specific Q&A chatbots to summarization and also compliance checking and things like that. So that was the, if you like, the generative AI part of the puzzle. The next thing is we're moving over to talk about agentic AI. And again, we have customers that want to run agentic AI, but running it at the edge is a challenge. Firstly, just to make sure we're all on the same page, we've defined agentic AI as an autonomous even, artificial intelligence system that can independently act on to predetermined goals without constant human insight. I like to think of it as basically it's a way of having the system work out what you want and then go and get the data for you. In terms of the key elements and the architecture, AI agents are independent. They keep running all the time, and they're semi-autonomous. You can have human-in-the-loop checkpoints, but they can run on their own. They're goal-oriented. They use natural language processing to actually have a sentence coming in from a human into the agent, and the agent then breaks that down, uses contextual reasoning, and creates a workflow for how to respond to the customer's response. And more importantly, with the agent, which is different to generative AI, it's continually learning as you go along. And one thing to consider as an architect is agents are token hungry. So you only want to use an agent where you really have to. You don't want to have agents everywhere because they are very expensive to run in terms of tokens per second, etc. And the main benefits really are adaptability, autonomy, and faster decisions in processes that may have difficult workflows. Just trying to work out some guidance as to what use cases agents are good for, because we're not saying agents are good for everything. Agents are good for tasks where customers are coming to them and asking them questions that they haven't seen before. They're good for creating workflows that are dynamic or created on the fly. And they basically work towards a task list, and they interact with other tools and other agents, so they can mesh with different tools. In our demo, we'll show that where we have an agent calling a generative AI system to create some text, but also to create an image. But also you should consider where the agents are less relevant. In a structured environment where there's little change, an agent is overkill. Or if the workflow is always the same, it's always the same pattern you go through, you don't need an agent for doing that. You can equip a normal generative AI application to do the same thing, or just a standard ML model. And the key thing here is if it's limited changes or you're cost sensitive, agents may not be the best starting point for your deployment. And one thing to bear in mind is hallucinations. In generative AI, hallucinations are bad. In an agent, if it goes off the rails, it can be really bad. So you always want to try and constrain the way the system's working and also how it behaves. So one of the things we recommend for agents at the edge, because it's a constrained compute environment, is running small language models as the inference engine. They're really good in terms of they can be specialized, so they can be a specialist SLM working in an agent. You can tailor it for each set of domains or operations, and they're very customizable, which is good. More importantly, you can control all the aspects of the agent in terms of how it behaves, what data it can see, etc. You can basically have a low infrastructure cost because the cost per token running an SLM is much, much lower, like 2 or 3% of the cost of an LLM. And you don't need the same number of GPUs at the edge to run it. And it's also highly performant, especially in terms of low latency. Some of the models are actually really quick at coming back with an answer, which is important for the agent. We've actually built the demo we're showing you here using the AWS Stands agents. And we've done that because it was pretty easy to use. It's actually a really robust set of capabilities. It's very extensible, and we've extended it into the edge, and it allows you to rapidly create an agent and deploy it. So that's just some, I'm not going into strands, but that's just some background as to how we built the agent. From an architecture point of view, we have the same setup again, where we have an application, and the application is doing the prompt engineering, checking the user, etc. That's then forwarded to the agent, and the agent break down what's inside the agent in the next slide. But we've also put in a semantic cache, because what we're seeing is a lot of times with an agent, the query or the question is similar to the one that's already been received. So you don't need to go through the whole workflow. You can just pull something from a semantic cache, and that gives quite a good saving in terms of costs. And then we can have human in the loop step, where a human needs to check off or click on something. And then we have a set of tools, and the key difference with an agentic architecture is the tools are recursively called. The agent can call the tools over and over again if it needs to. Whereas in a generative AI RAG system, the RAG database that I'm showing here will be called when the prompt is received, but it's not called again. Whereas an agent can actually pull data from the database over and over again. If it doesn't like the answer it's received from the RAG database, it can go back in again. It can also call other agents to do specialist tasks or tasks it's not equipped for, say maybe a maths agent or a graphics agent. And then it can call tools to do simple tasks like query a database or write some SQL query to get the data from the database, and can do that over and over again. Looking inside the components of the RAG database, we have the first step is to perceive or to understand the question that's coming in. The model needs to break down the text and say, if I'm asking for something, what does that mean? Then it goes through a reasoning stage where basically people go through, the workflow working with the SLM and a planning function creates an understanding of what the problem is and an understanding of how to address the problem. Then it has an act function that can actually go and call tools repeatedly, etc. It also has, importantly, memory. So it has short-term memory for the context of what it's doing, but also long-term memory to learn from the system, oversight, and learning, as I mentioned. I'll now hand over to a demo.
Thank you. So SLM works very well for specific domains. When you have a very defined domain, it's a thing that you can consider to use. In this demo, we can show a generative AI chef, the French Chef Antoine, when we can define some ingredients and they can prepare the recipe. Everything is running on EC2 as well. And everything is generated by AI. So I can select my protein. I have 4 steps here. I would like to select the beef. Now the enrichment sauce. So I would like to use olive oil, button mushrooms, and tomato. And the aromatics. So I can select here maybe this. And finally, we have the ingredients. And now, when I click here, we have a specific system prompt for the agent. The model that we are using is the same, is 5.4, meaning instruct. So we send to the model. The model will prepare the recipe and also prepare the image description, because I'll send this description to another model running to generate the image of this dish. So when I created here, prepare the recipe, you can see they choose boeuf bourguignon. Okay, we can see the recipe being created, including we have a chef tips, and we have a remarkable here at the end. 27 tokens per second was for this model, and here we see the image. This image is generated by one SLM. Based on this SLM, they send to another model to generate the image related to that. This is a naive Python application, but we also have Chef Amélie. Chef Amélie helps you to prepare, to organize your a party or one event at home. We have here in natural language, so I can ask, I'm hosting a casual Sunday lunch for 6 people. No one's vegetarian. Natural language in that case. But instead of show here, I'll show here. On this side, you can see the application log that we show. On this, we can see the application running. So, okay, this is an agentic AI application. We are using Strands Agents, SDK. Yeah? And you can see here, the SLM analyze the available tools And now they start using the tool, analyze menu requirement, calculate cooking time, generate shopping lists, all tools that we provide to this SLM model, to this application to send to the SLM model. And they decided which tool to use to combine all the information that they need to prepare the organization at the end. Including here, we have one that suggested wine pairing. So, and all the logs, of course, is happening here. And they will process the last part when they combine all this information and will prepare a final organization plan in that case. So again, we are using small models to process that. And let me increase. And here, casual Sunday lunch. So menu overview, we have starter, main, side, server 6 people, cooking timeline, shopping list that we use, the budget breakdown, in that case, wine pairing, they consider, and final notes, and some metrics that we have here. So the agent is running at the edge, is running on EC2s for a specific domain, in that case. So it's, of course, it's just a generic example, but you can consider inside the organization what makes sense for your application, okay? Hey, Chris.
Cool. So that was a summary of Agentic AI. What we've shown here is that it's absolutely possible and feasible to run Agentic AI at the edge on relatively small GPUs. The SLMs are the foundation of the whole system, and we've explained the architecture, and also we've looked at getting the TCO as low as possible for these systems. So summary overall, hopefully you've enjoyed listening to us about how we actually run SLMs at the edge. We've provided some best practices for this. We have blogs and also code samples that we've published if you want to look at this in more detail. Shared very quickly path to production and some of the steps we've gone through, and then talked about Agentic AI. So I'd like to thank you and ask, is there any questions?